Continuing on with our review of polar coordinates, we're going to be looking at graphing some polar equations. So let's look at some examples where we would potentially convert the given equation to rectangular form in order to graph it. So my first example is going to be the equation theta equals pi over 4. And I know that this is a polar equation because it has a theta in it versus an x or a y. So what I want to do here is I want to convert it to rectangular form so that it does have x, y's in it. And then I can graph it on the rectangular grid. So one strategy that we have is that we can take the tangent of both sides of the equation. And the reason that I would do that is because the tangent of theta has a special connection to rectangular. So we know that theta is equal to the inverse tangent of y over x, which means that the tangent of theta itself is equal to y over x. So if I took the tangent of both sides, now I can make a direct substitution for the tangent of theta and rewrite it as y over x. So the goal in converting this equation from polar form to rectangular form is to get rid of any thetas or r's and create a new equation that has only y's and x's. So y over x equals the tangent of pi over 4. Well, I can simplify that even further since I know what the tangent of pi over 4 is. And the tangent of pi over 4 is 1. So we now have a rectangular equation. But to graph that equation, we know that in rectangular form, we always want it in y equals form. So if I multiply both sides by x, I'm going to get y equals x. So let's look at graphing this function. And again, since it is in rectangular form, I'm going to use a rectangular grid to graph it. So we know that it's a line, and it has a slope of 1 and a y-intercept of 0. So a y-intercept of 0 gives me a point 0, 0. A slope of 1 means I'm going to go up 1 and over 1. And I can continue to do that until I create this line. So this graph here represents the graph of y equals x, but it also represents the graph of the tangent. Sorry, it doesn't represent the graph. The tangent represents the graph of theta equals pi over 4. So there's one example. Let's look at another. In this example, we're also going to have a line. It'll be a different type of line though. So r sine theta equals 2. Again, we know it's a polar equation because it has r's and thetas. And one possibility to graph it is to change it to rectangular form. So, r sine theta is actually the exact same thing in our conversion formulas as y. So I could convert this formula into rectangular form in one quick and easy step. Y equals 2. Of course, we know that when we graph y equals 2 on a rectangular grid, it's just a horizontal line at 2. So this is the line y equals 2, but it also represents r sine theta equals 2. Okay, so those are both linear, and again I would describe this as a horizontal line through the point y equals 2. which hopefully we remember has a slope of 0 and a y-intercept of 2. Let's look at something that's nonlinear, because that is much more typical of a polar equation. A lot of times they're going to give us curves. So let's look at something that will be circular. So let's start off with the polar equation r equals 4 sine theta. And again, let's convert it to rectangular form. Well, you can see that up here I had r times the sine of theta, which gave me y. Here I don't quite have that. I've got 4 times the sine of theta. So that's not exactly y. But if I were to multiply both sides by r, then I could get y. Okay, so let's see what that does to the left side of the equation. If I multiply that by r, that gives me r squared. So you want to think about, is there a substitution that you can make in rectangular form for r squared? And there is. X squared plus y squared. So this is the rectangular form of the equation. And it's our job now to graph it on a rectangular grid. The problem is that it's not a function. Okay, so we have a y squared, which makes it not a function. It's going to actually be a circle. And so we can't put it in y equals form the way that we did with the way that we would with a function or with a line. Instead, what we would do here is we would complete the square. So that is something that you have to refer back to, completing the square. And to do it with circles, you have to do it sort of in 2 groups. You have to do it with your x's and with your y's. So if I take that 4y term and subtract it over, I'm going to group it with the y squared, and I'm going to complete the square here. Over here we actually don't need to complete the square. The x squared will stand alone. It doesn't have an x term with it. So over here, in order to find the center of the circle, again, I'm going to complete the square. So I'm going to take half of my coefficient of y, and then I'm going to subtract that value squared away. So that leaves me with x squared plus y minus 2 squared equals 4. And this is the general form of a circle, where the center of the circle is going to be at the point 0, 2, and the radius is going to be 2. So now I can plot that point on my rectangular grid. Or not plot that point, I mean graph that equation, graph that circle. So remember, the center of my circle is at 0, 2. And I have a radius of 2 that will go in every direction, giving me a circle. Alright, so that is another way that we can convert into rectangular form in order to graph a polar equation. But sometimes they're not linear, sometimes they're circles, and we need to do some work of completing the square so that we know the center and the radius of that circle. Let me also bring the graphing calculator into this discussion at this point, and let me show you how to graph this same thing on a graphing calculator. So first things first, you need to change your mode. So you can see that mine already is in polar, but typically yours would be in function mode. Parametric mode is not something we're going to use, but here's polar mode. So put your graphing calculators into that polar mode. And instead of y equals, when we go to this menu here, we will have r equals. So if I type in r equals 4 sine theta, and I found theta by just pressing the normal x key. Now that I'm in polar mode, it knows that I don't need an x, I need a theta. As far as my window, you may want to play around with that a little bit if you already know what your window is going to be. If not, you can just test it out and see what it looks like. And there we get that same circle centered at the point 0, 2 with a radius of 2. So we can graph polar equations by converting them to rectangular form. We can also use our graphing calculator to see that graph without converting at all. Okay, so sometimes it's not that easy to convert, and sometimes it's nearly impossible to convert. And again, the graphing calculator can be very helpful in that scenario. But let's take a look at another example here. Let's see, I left off on number 3, so this would be number 4. R equals 1 minus the sine of theta. You could try to convert this to rectangular form. It's not going to go so well. Multiplying by r is going to cause problems. It's really tough on this one to get rid of r and theta and make some direct substitutions for x and y. So that's why we have some other approaches that might work as well. So let's say we wanted to plot some points. So we need some different theta values to give us some different r values, and then we could plot those points. So let's start with theta equals 0. And you have to use your trig, your unit circle. The sine of 0 is 0. And my r is 1. Let's try theta equals pi over 6. So I'll get r equals 1 minus the sine of pi over 6. And the sine of pi over 6 is 1/2. So my r is 1/2. And I could continue and do many, many, many different theta values until I could plot enough points to see what the graph would look like. Sine of pi over 4 is going to be the square root of 2 over 2. So 1 minus the square root of 2 over 2 is going to be 2 minus the square root of 2 over 2. And of course we need to approximate that because we're not going to be able to plot that point as is. So it's approximately 0.3. The other thing to keep in mind is that you may want to skip any angles that aren't going to give you nice values. So it's your choice in terms of making your table, what theta values you want to use. You certainly don't have to use pi over 4 if it's not going to give you a nice value. So anyway, you would take your polar grid and you'd start plotting some points. So at theta equals 0, r equals 1. At theta equals pi over 6, r equals 1/2. Certainly not enough points for me to see the entire graph. But to keep the video short, I'll just say you would continue, you'd plot more points, and you'd get a graph. However, the graphing calculator does become a big help in this scenario. If I were to plot or graph the given equation, it's obviously going to help me visualize what my points are, or what my overall graph is going to look like when I connect my points. So I could get those specific points using a table, and then I could use the graphing calculator to help me connect them a little bit better. So here's what we have. I'm going to minimize the window a little bit to try to zoom in on it, and maybe even more. And it's just a little slow to finish off. Okay. The other thing that you can see I just did was z squared. Squares off my window. Oops, I must have done something with my angle that's messing that up. But at any rate, you could put your table that you're making, plotting points together with your graphing calculator, and create a graph of a polar equation that way as well.